In exercise 912, we're going to draw the mechanism for acid-catalyzed hydration. Now, just like if you add water to yourself, then you are hydrating. So likewise, if you add water, now we're going to add it in as two things, H and OH, but notice altogether that's HOH or H2O. Altogether that's water, and so we're going to add H and OH across a double bond. In other words, we're going to add water to the double bond, and so that's going to be hydration. Now, it says acid catalyzed. A catalyst is something that doesn't get used up in a reaction, it just helps the reaction happen faster. So if it's used in a first step, then it'll be produced in the last step, and that's what ends up happening in these reactions. And so an acid is going to be the catalyst. So if you look over the arrow for these three different reactions, you'll see that acid-catalyzed hydration represented in a few different ways. In each case, you're going to have water, and you're going to have H3O+. Both of those will be present. Now, sometimes they may just mention that as H3O+. If H3O+ is present, sometimes it breaks apart and turns into water. And so if you have H3O+, there is also water there. Another way they can show it to you is they can have dilute acid, and it could be technically any acid, but a common acid is sulfuric acid, H2SO4. And dilute just means that it's not pure sulfuric acid, it's diluted with water, so it's H2SO4 and water. So acid and water. And a third way that they may show it to you is in C here. You have the water, and then in this particular book, and this is kind of a convention that really is unique to this book, but you may see it somewhere else. They're using brackets with the reagent, brackets next to the arrow. Those brackets are saying this is a catalyst. Now inside those brackets can be different things, but in this exercise, because it's acid catalyzed, it's H+ inside of those brackets. So that's just saying this is an acid, H+, that's acting as a catalyst, brackets. Okay, so in each of these cases we're adding water and an acid, and that can be represented in slightly different ways. So let's walk through the mechanism for this individually for each one of these. Starting with this first one. There will be some similarities between this and the mechanism for hydrohalogenation. For example, the pi bond will again be our nucleophile. Our electrophile here, though, is going to be the only molecule they're giving us, and that is hydronium. And for all of these mechanisms, no matter what they give you in terms of the acid, because water will always be there, the acid will give an H+ to the water, and you can start with hydronium, H3O+. So if you were to look at this and say, what would this nucleophile attack in this first step? You might be tempted to say the oxygen. I mean, after all, the oxygen does have a full positive charge. So that would seem like a good electrophile. Notice that the oxygen already has 2, 4, 6, 8 electrons around it, and that it can only have 8 electrons around it. That's because an oxygen only has 1 s orbital and 3 p orbitals. Now, each of these can hold 2 electrons, so 2 plus 2 plus 2 plus 2 is 8. And so that's the origin of the octet rule, the 2 electrons in each of these orbitals and only having s and p orbitals. And so that is the case for oxygen, and so oxygen can only have 8 electrons. So you can't just form a new bond to this oxygen. If you form a new bond to the oxygen, you'd have to break one of the bonds that are already there. In other words, you would have to kick off one of the hydrogens. But is hydrogen a good leaving group? Imagine it taking its electrons and leaving the molecule. In that case, you would have a hydrogen with 2 electrons and a full negative charge. Is the hydrogen able to stabilize that negative charge? It's not, because hydrogen is the smallest atom on the periodic table. And to fit a full negative charge in that tiny, tiny space, the charge will repel itself and make the hydrogen very unstable. So that's a terrible leaving group. It's very unstable after it leaves the molecule, and so it's not. So although there's a full positive charge on the oxygen, it's misleading because that is not a functional electrophile. It already has the full number of electrons it can, the oxygen, 8 electrons, and it can't kick anything off because all of the hydrogens that are there are terrible leaving groups. Okay, that's when they take their electrons with them. And so our nucleophile cannot attack the oxygen. But there are other things there for it to attack in this hydronium, namely the hydrogens. Now, anytime a hydrogen is bonded to an oxygen, it loses electron density to the oxygen. And so it becomes slightly positive. So each of these hydrogens is slightly positive. Excuse me. But that slight positive charge is actually very big here, because in addition to just the electronegativity of the oxygen pulling electrons toward itself, in addition to that, the positive charge on the oxygen is attracting the electrons even more. And so the electrons really, really, really go to the oxygen, and these partial charges are actually really big. They're almost full they're almost full charges. So those hydrogens are very attractive electrophiles. They're vulnerable. Hydrogens are always on the outside of a molecule, so they're exposed to the outside world. They bump into stuff a lot, and they have a really slightly positive charge in this molecule. So our nucleophile attacks one of those hydrogens, and the electrons that were attached to the hydrogen snap back onto the oxygen to help stabilize the positive charge. And so after that step, you would have same carbon skeleton. And we'll think about what happens to the hydrogen in a second. We have the same oxygen with the 2 hydrogens that weren't involved, the 1 lone pair that was there before, and now this bond becomes a second lone pair. So hydronium turns into water. Okay, now this hydrogen is going to add to this molecule. But where does it add? You could imagine it going in two places. You could imagine the hydrogen attaching to this carbon on the right. Now in that case, the carbon in the middle, which had those pi electrons, doesn't have it anymore. It's missing electrons, and so it has a positive charge. Or the hydrogen could have gone in the middle, and in that case, the carbon on the right side of the double bond had the pi electrons. It doesn't have them anymore, so it's missing electrons. It would have a full positive charge. So we've seen an analysis kind of like this in hydrohalogenation. And in hydrohalogenation, we came up with Markovnikov's rule. Markovnikov's rule said that hydrogen goes to the less substituted carbon. And the reason for it was because that gives you the more stable carbocation. If you're trying to assess which of these two structures would be more likely to form, think about which one is more stable. And the thing that's making these molecules unstable is the full positive charge. So which positive charge is more stable? Well, they're carbocations. This carbon on the left, the carbocation is bonded to 1, 2, 3 carbons. So that is tertiary. The carbon on the right is bonded to 1, 2 carbons. So that is secondary. The more stable carbocation is the more substituted one. And so this carbocation on the left is the one that's going to form. And so the hydrogen goes on the other, less substituted position. Okay, and once again, when hydrogen goes to the less substituted position so that you will get the more stable carbocation, that is known as Markovnikov's rule. If you know any Russian, Markovnikov's rule is kind of funny after the last chapter where we learned about Zaitsev, the Zaitsev product. In Russian, Zaitsev means rabbit, and Markovnikov means carrot. These were just scientists' last names, but it's a funny coincidence. Okay. So this acid-catalyzed hydration is going to be Markovnikov addition because the hydrogen is going to add to the less substituted carbon in order to give you the more stable carbocation. Okay, well now and before we move on, let's just look back at this. as you go through these curved arrow patterns, as you go through these mechanisms, anytime you show some sort of thing happening, always try to classify it or categorize it in one of those 4 curved arrow patterns that we learned. Right now, these mechanisms are manageable. They're maybe 3 or 4 steps long. But in organic chemistry 2, and as this course goes on, the mechanisms can become very long. They can become 9 steps long. And so it's useful to be able to build a habit of summarizing them within those 4 curved arrow patterns. Now in this one, you see, in this first step, you see a hydrogen transferring from one molecule, the hydronium, to another, the carbon chain. And so when you transfer a hydrogen from one molecule to another, that is a proton transfer. Remember, a hydrogen just has one proton in its nucleus, and so hydrogen and proton are often used synonymously. Okay, so that's that first step, a proton transfer. Pi bond attacks the acid. In the next step, if you're stuck here, you're like, I have no idea how these two things would react, go through the same analysis that we did before. Anytime you're stuck, locate electrophiles and nucleophiles. We have a really good electrophile on our carbon, the carbocation. And the oxygen in water is a nucleophile. The oxygen is very electronegative, so it pulls electrons to itself and becomes slightly negative. And then those hydrogens, of course, would lose those electrons and become slightly positive. So the oxygen has a slight negative charge, and it has lone pairs. Those are all signs that it can act as a nucleophile. So it swoops in and attacks the electrophilic carbon. So if you were going to classify that curved arrow pattern, that would be nucleophilic attack. All right. So we have that same carbon skeleton. None of the sigma bonds broke. We still have that methyl group there, but now we're going to have an oxygen that's bonded to 2 hydrogens. Notice it will only have one of its lone pairs left. The other lone pair is going to go to form the bond. Whenever oxygen has 3 bonds, it has a full positive charge. It's called an oxonium ion, when oxygen has 3 bonds and a full positive charge. We saw that here in hydronium, when the oxygen is bonded to 3 hydrogens, but in this case, it's bonded to 2 hydrogens and a carbon. Doesn't matter, 3 bonds overall, and the oxygen has a full positive charge. Okay, well, notice in this nucleophilic attack, we started with a nucleophile that was neutral. We saw this when we were drawing those complex SN1 mechanisms. In those complex SN1 mechanisms, at the very end, you would sometimes have to do a proton transfer. And the reason you had to do a proton transfer was if you had a nucleophile that was neutral. If you have a nucleophile that's neutral and you start forcing it to share electrons, to lose some of those electron density, share it with another atom, well, then it becomes positive. In other words, if you have a neutral nucleophile, it becomes positive after the nucleophilic attack. And the way that you stabilize charge is through proton transfers. If you have a positive charge, you can get rid of it by donating an H+. If you have a negative charge, you can stabilize it by accepting an H+. And so donating or accepting H+, those are proton transfers, and you can stabilize charge by doing proton transfers. And that's exactly what happens here. A water molecule from the solution comes in, and the oxygen has the lone pairs. The oxygen also has a slightly negative charge. The hydrogens have a slightly positive charge. The hydrogens here also have a slightly positive charge, especially because the oxygen has a positive charge. The oxygen is pulling electrons to itself just because of its electronegativity, but the positive charge is making it pull electrons even more, so this is really slightly positive. And the oxygen in the water steals one of those hydrogens. The electrons here snap back onto the oxygen to help stabilize the positive charge there. And you end up with 2 things. First, when water accepts that H without the electrons, that H+, water turns in to hydronium. Now notice it had 2 lone pairs, now it's just going to have the 1. the other lone pair turned into a bond. And anytime oxygen has 3 bonds, it'll have a positive charge. So we have hydronium, and then we have our carbon skeleton with an oxygen that has only 1 hydrogen. It had 1 lone pair before. This bond turns into a second lone pair. And so we end up with these 2 molecules. First, we end up with an alcohol. So we added H and OH, and we end up with this alcohol. And second, we end up with hydronium. Now notice, we started with hydronium. Oops. We started with hydronium. And we end with hydronium. That means that hydronium does not get used up. Sure, it helps the reaction to happen, but for every molecule of hydronium that's used, a molecule of hydronium is produced. A molecule that makes the reaction happen, but doesn't get used up, is known as a catalyst. Now in this case, that's different from a reagent, because the reagents get used up. A catalyst does not get used up. And so in this case, the catalyst is an acid, hydronium, and so it's acid catalyzed. Notice also we added 2 things. We added an H, that was to this hydrogen, to that carbon there, and we added an OH. H into OH, that's water, that's hydration. So in the mechanism for acid catalyzed hydration, if you are thinking of it in terms of curved arrows, you have first a proton transfer, next nucleophilic attack, and finally, in this last 3rd step, we're transferring a hydrogen from one molecule to another, the carbon to a water, so that's another proton transfer. So acid catalyzed hydration is really a nucleophilic attack sandwiched in between 2 proton transfers. And it's much easier to remember that than to try to memorize every single one of these arrows, although you'll need to do that too. But having this scaffolding there for you will help you to keep track of which arrows need to move. All right, so we went in some detail on that one. We went pretty slowly through it. Let's just quickly draw that same mechanism with a couple other carbon chains. So first, this one here. Now you'll remember the pi bond is your nucleophile. And here, they give us dilute H2SO4. Now, H2SO4 is a strong acid. Right? We've seen that before. It's a sulfur with a double bond to oxygen going up and down, single bond to oxygen going left and right, and then single bond to hydrogen going left and right. And it's such a strong acid because you can remove a hydrogen without any electrons, so an H+, and the bond will snap back onto the oxygen to have a negative charge there. And that lone pair, that negative charge, is stabilized through resonance. It's allylic to 2 pi bonds. And because it's stabilized through so much resonance, it's really stable, and so this acid can leave very easily. In other words, sulfuric acid is a very strong acid. And so when you put sulfuric acid into water, almost all of its H's come off. They're scraped right off, and the H+'s end up going on to a water molecule. So one of these lone pairs attracts the H+, and so you end up with hydronium. So, and that's what the fact that they say dilute, that means you had that water to begin with. So you could just start the mechanism with hydronium. You don't have to draw the H2SO4 here. If you see dilute H2SO4, you know you have hydronium in that solution. And as we saw, the hydrogens in hydronium are slightly positive, and they're the only thing that can be attacked here. The oxygen already has a full octet, and it has no good leaving groups on it. So the pi electrons attack one of those hydrogens, and the electrons in the bond that we're holding the hydrogen on snap back onto the oxygen to help stabilize that positive charge. So that is our first step, the first proton transfer. So once you have that, we know this is Markovnikov addition. Now first, hydronium is going to turn into water. It lost one of those H's. The electrons in the bond turn into a second lone pair. We're going to add the hydrogen, and we know this is Markovnikov addition. Markovnikov addition tells you that the hydrogen goes to the less substituted carbon. This carbon here is tertiary. The other carbon in the double bond, right, this one, was primary. And so the hydrogen goes to the less substituted carbon. It's this one, this primary one here. Now that means that the carbon that was in the middle, the more substituted one, that had pi electrons, and now it doesn't anymore, and so it's missing electrons, and so it will have a full positive charge. So we end up with that tertiary carbocation. So Markovnikov addition, H goes to the less substituted carbon. Well, now the oxygen in water has a slight negative charge. The lone pairs are also another sign that it's a nucleophile. And so that nucleophilic oxygen attacks the electrophilic carbonyl carbon. So this is our middle nucleophilic attack. That nucleophilic attack that's sandwiched in between two proton transfers in acid catalyzed hydration. And once that's done, you'll have that methyl group there still, but you'll have an oxygen still bonded to two hydrogens with just one lone pair and a full positive charge. That's that oxonium ion. Anytime oxygen has 3 bonds, it'll have that full positive charge. And to stabilize charges, you do a proton transfer. So we're going to do another proton transfer here. So you take another water from the solution. One of the lone pairs on that slightly negative oxygen attack the slightly positive hydrogens. So it attacks one of those. The electrons snap onto the oxygen that has the positive charge to help stabilize that. And you end up with an alcohol. That's a molecule that has an OH on it. In addition to hydronium. So again, we started with hydronium. We end with hydronium. Hydronium does not get used up. The molecule that makes the reaction happen without getting used up is a catalyst. And we did Markovnikov addition of H and OH. The H went on the less substituted carbon, the OH went on the more substituted carbon. The overall mechanism was 2 proton transfers with a nucleophilic attack sandwiched in between. All right, let's see that play out in one last one. Notice as we draw these, notice that the reactivity of the molecule has everything to do with the functional group, in this case, the pi bond, the alkene. And it doesn't matter, kind of, what the carbon chain is. Now, that's not always true, right? The carbon chain certainly adds a new shape to the molecule, and we're producing these carbocations here, so really, you should always be checking to make sure that these carbocations won't rearrange. For example, here we have a tertiary one, and all the positions nearby are less substituted, primary, secondary, secondary. Or again, here, we have a tertiary carbocation, and all the positions nearby are less substituted, primary, primary, and primary, so they won't rearrange. We should be checking for that. But there's something very beautiful here about seeing that the reactivity has everything to do with that pi bond and nothing to do with the rest of the molecule. So that if you know that adding hydronium and water and to an alkene, if you know what that does, it adds H and OH in a Markovnikov way with possible carbocation rearrangement. You can take molecules that you've never seen before, and you'll know how they'll react. So that's why organic chemistry is organized based on functional groups. Because even though there are an infinite number of molecules, which no one would ever be able to learn all of, if you know how a functional group behaves, you will know how it behaves on any molecule that you run into. Okay, so again, we know this carbonyl, the pi bond, this pi bond here is going to be our nucleophile in the case of hydronium, and notice that is what we have here. We have water, but it's with an acid catalyst, so that those brackets with the H plus are just like having the H2SO4 there. Add an H plus to water, you get hydronium. So that's what we're doing here. You can start with the hydronium. Each of the hydrogens in hydronium is slightly positive. They're losing their electron density to the oxygen, which is very electronegative. And so the nucleophilic pi bonds attack, the nucleophilic pi electrons attack the hydrogen. The electrons that are in the bonds snap back onto the oxygen to help stabilize that positive charge. And that is proton transfer. We're moving a hydrogen from one molecule to another. So the hydronium is going to turn into water. We still have this bottom half. The bond turns into a second lone pair. And the carbon chain, the sigma bonds will all be the same, but we're going to add a hydrogen on there, and because this is Markovnikov addition, we're going to add the hydrogen to the less substituted carbon in the double bond. So this carbon here, that is tertiary, it's bonded to 1, 2, 3 other carbons. The other carbon in the double bond is only bonded to one carbon, so that's primary, so the less substituted is the primary one. And that's where the hydrogen goes, because this is Markovnikov addition. And that means that this other carbon, which had those pi electrons, is missing them now. And so it has a full positive charge. So we have a tertiary carbocation. And technically, anytime you have a carbocation, you should check for carbocation rearrangements. Now this is tertiary right now. Next door you have primary, secondary, and secondary. So it's already on the most stable position, and it won't rearrange. The oxygen in the water has a slight negative charge. It's stealing electron density from those hydrogens. Each of these are slightly positive. The slight negative charge, in addition to the lone pairs, make the oxygen nucleophilic. And so that nucleophile attacks the electrophilic carbocation. And so that is our nucleophilic attack. So that nucleophilic attack, we know in acid catalyzed hydration, that's sandwiched in between two proton transfers. So here we will end up with our carbon skeleton, and now we'll have this oxygen bonded to two hydrogens attached. Anytime oxygen has 3 bonds total, it'll have that positive charge. It'll be that oxonium ion. So that's our molecule. You'll notice that we have a positive charge there, and you stabilize charges by doing proton transfers. And so that's what we're going to have here at the end, a proton transfer. We have a positive charge, so we're going to get rid of an H+, and that will stabilize that molecule. In other words, we have to add a base to this, and water is going to act as our base. It's going to accept an H+. The oxygen is slightly negative, and it has these lone pairs, and the hydrogens on the other molecule, no, the hydrogens on this molecule too, but the hydrogen, significantly for the reaction, the hydrogens on the other molecule are slightly positive, and so this oxygen is going to attack one of those. The electrons in the bond that was holding onto it will snap back onto the oxygen to help stabilize the positive charge on it, and you will have the oxygen with just one hydrogen. Any molecule that has an OH attached to it is called an alcohol. So that's what we have here, and then we'll have H3O+. We had water, it accepted an H+, so now it's H3O+. And so just notice those big features again. We started with hydronium and we end with hydronium. And so hydronium, a molecule that allows the reaction to happen but does not get used up, is a catalyst. And ultimately, the effect that the reaction had is we got rid of those pi electrons, or rather those pi electrons were used as molecular glue to stick a hydrogen onto the molecule. And we ended up adding a hydrogen and an OH. The hydrogen went to the less substituted carbon. The OH went to the more substituted carbon, and that's Markovnikov addition. Overall, if you had to classify this in your mind with those big pattern, curved arrow patterns, it's two proton transfers sandwiching a nucleophilic attack in between them. So proton transfer, nucleophilic attack, proton transfer. So hopefully you could see some parallels between this and hydrohalogenation, and hopefully this video helped a little bit with drawing the mechanism for acid-catalyzed hydration.